Oh, smart guy. All right. Oh, what am I doing wrong? It's not going to sit down. Yeah, all right, so I like to point that out. Also, another thing about that demo I really like is it forces us to realize that water is not different than, I mean, obviously water has different properties than its desktop, right? But it obeys the same laws of physics. You throw some water in the air and undergoes parabolic projectile motion, just like I would if you threw me in the air, right? Even though, and actually I am mostly made of water, but even if I weren't, right, if we read biology, if you throw a rock in the air, it follows the same projectile motion trajectory, right? And that's important. Laws of physics are the same for water. They have to be the same laws as the rest of us, and students don't believe it. So I'll do some demos. When we get to fluid later in this class, I'll show you some demos that will probably surprise you, because people don't want to believe that water follows the same rules, but it does. One last thing I want to point out before we leave projectile motion to move on to forces is that I've been mostly using pictures. So I've been doing two kinds of pictures. I start off with a picture of the physical situation in space. I have x versus y. And I've been sort of drawing these parabolas. And oh, yeah, I know this is parabola, right? But I have never actually calculated for you that it's really a parabolic shape you get. The things that we did carefully were thinking about x versus t, v versus t, a versus t, right? So how do you get x versus y, and show that it's a parabola? I think you guys all know this, but I mean, the basic point is this, that whenever you have projectile motion, so there's acceleration in the downward direction, right? You've got some, so you have some object, right? It's y position, you have some initial y position, right? And then you add to it whatever the initial y component of the velocity was, right? So v sub y0, right? And then you add to it minus 1/2 gt squared. And this, of course, assumes upward is positive y. Oh, what did I get wrong? Oh, yeah, my units are totally wrong. So right? Correct. Yes, that's right. So great. I think that looks okay. And the convention I must have chosen here, given I got a minus sign here, is that I meant to go like this positive upward for y, x is doing this. What does x look like? Well, for projectile motion, there's some initial position for x, and then you've got some initial velocity in the x direction, right, times t, thank you very much. And then we add nothing for acceleration, because there's no acceleration in the x direction. So if you choose to represent some projectile motion with x and y being horizontal and vertical, respectively, and you choose upward to be the positive direction for your y-axis, then this is what you get. If you then combine these equations and say, can I write y as a function of x? I'm not going to go through all the algebra, you have all these terms that fly around, but you can see what you get, right? There's only one t squared piece in these equations, in the y up here in y. If I stick in, if I isolate for t over here, what do I get? I get that t equals some difference in positions over a velocity. That's what I have to get, right? Because this is meters per second, that's meters, that gives me second overall, so good. I can substitute this then in, back into the y equation, and that's how it is you get a parabola, right? Just formally, how do you calculate this? You do that, and then what you wind up with when the dust clears is that, I'm not even going to write it in terms of the original variables, I'm just going to write it in general form. So, well, you get some constant, right, minus some other constant, well, it's too easy. Some constant minus some other constant times some x minus x prime, whatever that is, squared. You get, in other words, you get a downward-facing parabola. You get this, right? And that's formally, and also we talked last time, students came out there and said, what were you talking about with that? The two possible axis angles, the two different axes of symmetry of the ball that's being shot from the cart. Well, the point is when you have projectile motion, or this is what's describing the y and the x, those are the equations of motion in vertical and horizontal direction. You always wind up with a parabola that's facing downward, and it's got an axis of symmetry that's vertical, right? So you get an equation like this. Anyway, just so it's clear where that comes from. And why do you call it a parabola? Anything of the form y equals a constant plus a linear term plus a second, a quadratic or second order term, and your dependent variable, that's called a parabola. That's just the conic section that, yeah, you guys know that stuff. Anyway, so that's where all that came from. Just to be pedantically clear where all that stuff comes from. All right, projectile motion. You've done a lot of that, and you're doing it for your homework, and you'll see it again and again, and it'll probably show up in the first midterm. What's the, oh yeah, and there's one more topic about describing motion I should cover really quickly, because it trips students up a lot, before we get on to forces. And that is relative motion. Now, you all have really good intuition about relative motion in some contexts. For example, probably most of you have good intuition for all contexts. It's just a matter of getting the notation on your equations to agree with your intuition. If you're on a bus, and the bus is going that way, let's say I'm on a bus is going that way, and I have a piece of chalk in my hand, and the bus is going 60 miles an hour, and I throw the chalk forward in the bus. And with my arm, I can throw it at 90 miles, no, I'll say 10 miles an hour, all right? 10 miles an hour forward on the bus, relative to the bus. Well, if the bus is going 60 miles an hour that way, and I'm sitting on the bus and I throw it 10 miles an hour relative to the bus, how fast is the chalk moving relative to the ground? 70 miles an hour. How'd you do that? 60 plus 10 is 70. That's all you have to do, right? What if I'm facing backward? Bus is going that way, I'm not feeling, but it's okay, and I throw the chalk that way 10 miles an hour. So relative to the ground, how fast is the chalk moving? 50, 60 minus 10. And which way is the chalk going relative to the ground? That way or that way? Yeah, it's going that way. Because it's 60 minus 10, yeah, it's mostly going that way still. You get a positive number out for the velocity, right? For the x component of the velocity. So you all know how to think about relative velocity in one dimension, and you can get it right without even doing any pencil and paper, right? What a lot of students stop is thinking about it as vectors. But you also know this. You're flying on an airplane, right? You're on an airplane, you're going this way, all right? Here's your plane, just sort of a small plane, sorry. And it's old-fashioned vectors. Right? Okay, you're going that way, and you're going at some velocity relative to the air, okay? I'm going to try to get my notation so it agrees with the book's notation. So let's call this v. This is your velocity of, what's the book's notation? Oh, yeah, there we go. Plane with respect to, so it uses a capital V for wind versus the ground. So let's do this. Here's my capital V. So by this I mean this is wind with respect to ground. This is the velocity of the plane with respect to the air. So then what's the resulting velocity be? So I'm just drawing this vector right through the plane. Sure. This is where the vector starts, here's where it ends. Here's where the vector starts, here's where it ends. Well, the result is going to be that you're not going to move with respect to the ground straight that way. I mean, suppose this is east, west, north, and south, right? This is east, north, just so I can put names on in different directions. So right now the plane, the pilot is aiming his plane, or for plane, due east, right? But there's a wind. Actually, that's referred to as a northerly wind. It's kind of strange. It's coming from the north. But we'll say the wind is moving in a southern direction. Does that make sense? Wind's going down in the picture. Plane's trying to go straight right. It's doing that relative to the air. So which way is the plane going to go relative to the ground? Going to go up to the right, down to the right, down to the left, up to the left, down to the right. This is what the plane's going to actually do with respect to the ground. That's the velocity. I think they call it v. Oh, okay. They call this v prime in the text. Doesn't matter. But I just want to keep it the same so you can look it up later and sort of make sense of what I did relative to what the book says. So this right here is the velocity of the plane. I like subscripts. That's why I keep it clear. Right? P means plane, right? This is plane with respect to the ground. This is the resulting velocity of the plane with respect to the ground. And all I did was add vectors. I'll raise it up for a second so people can see over this thing. Right? Plane's trying to go straight that way. Wind's blowing straight down. The resulting velocity of the plane with respect to the ground is like that. And is this, so is in this particular scenario, is the speed of the plane greater with respect to the ground or with respect to the air? I heard people say it, but so what do I mean by speed? I mean the length of the velocity vector. Is this vector longer than that vector? Yeah, it is because this happens to be a right angle given the way I set the problem up. It didn't have to be that way. Like the case with the apple thrown inside the bus, right? You throw the apple in the bus, you throw it forward in the bus, then the apple's moving faster with respect to the ground than it is with respect to the bus. If you throw it backward in the bus, it goes the other way. So it depends on exactly what the different velocities are in the problem. But in this particular case, if they're in orthogonal directions, then yeah, the resulting vector of the plane's velocity with respect to the ground is the greatest speed, well, has the greatest length of the problem, the greatest speed of the problem. Great. So that's what we mean by vector addition. This is what we mean by relative velocity. That when you're describing the motion of something, you can describe it with respect to any number of different reference frames. You have a choice about what reference frame you're going to use. Now, you don't have infinite choice here. I did kind of a strange thing in this last problem, because at the end I gave you some intuition about what would happen if I had a camera that was falling from the ceiling. It was accelerating. So the reason that's a little strange is that we're getting into forces at the end of this, toward this lecture. I'm just about to move into this, and for the rest of the class, when we start talking about forces and physical laws that describe how to relate forces to accelerations of objects, Newton's laws, in other words, then we get into trouble unless we use inertial reference frames. So if you're on board a bus that's accelerating, so suppose the driver stops on the gas and the bus is accelerating, you know from experience, right, that suppose you have an apple sitting on the ground, apple sitting on your little tray, in front of you, you can eat it, right? The apple sitting there. When the bus driver hits the gas, the apple might start spontaneously rolling and roll off the back of the tray. Well, Newton's second law, which I'm trying to mimic, myself. Well, it would say that shouldn't happen. But in other words, if there's no force acting on the apple, it shouldn't accelerate. But the reason you're getting a strange answer there is you're measuring it in a reference frame that's not inertial. Well, okay, so I'll stop getting ahead of myself and just go ahead and introduce the forces. The point is that was a really useful thing to describe what it would look like from a perspective that makes clear why the ball hits the monkey. But it's not a reference frame that's valid if you want to apply Newton's laws. All right, so what are Newton's laws? He's got 3 of them that we'll use in this class. In fact, we only need 2. Newton's first law is really, as far as this class is concerned, it's really just a special case of Newton's second law. Newton's first law just says that if an object is moving along with some uniform motion, and nothing acts on it, it's going to keep doing that. It's not going to stop moving. It's going to keep moving the same way it already was. That's a special case of his second law. Should I give you background? I'll take it real quick. This was figured out a couple hundred years ago, more than that, but not by much. 2,300 years ago. What do people think? Well, Aristotle and people in that school of thought, Aristotle in particular, whose brain survives, we can see that he came up with these ideas, said, look, what's special is you can constantly move by pushing it or throwing it. And then the sort of vitality, the sort of vital force inside this thing is going to leak away and it stops moving. So as the book nicely describes in a few sentences at the beginning of chapter 4, it says, look, in the old days, people thought the big question was what makes things move. And Galileo's insight, which was around 1600, was that really the question is what makes them change their motion. You don't need to worry about what makes them keep moving. That's sort of a natural state of affairs. They keep moving. What's special is when things come in and interfere and make things stop moving or change their motion. So the real question is what causes changes in motion. And Newton came along and said, let's introduce these notions of force and really carefully work this out. He invented calculus and everything else. Just in order to solve the problems in motion plans. Anyway, very good stuff. The point is that forces, if there's no forces acting on something, it will keep moving as it was. If you have a ball that's rolling along with a shark rolling along on the table and there's no force acting on it, it'll just keep right on rolling. What kept giving trouble to Aristotle and 2,000 years of thinkers who didn't understand this was that when you are in the real world and you've got some rock in your hand and you throw it, there's all kinds of forces acting on the rock. The hard thing about physics is trying to isolate something so that there's nothing acting on it except the one thing you're trying to study. So when Aristotle would take a piece of chalk or rock or whatever and throw it, it would bounce on the ground and come to a stop. Well, yeah, because there's friction and there's wind resistance and there's forces acting on the object. But he didn't really know about those things. He says, okay, I guess the thing that was making it move left. Right? But the way to really think about it is that if there's no forces acting on something, which is a really bizarre situation, it doesn't happen much in our day-to-day life, it'll just keep on moving as it was, in a straight line forever and ever. It won't slow down or speed up, it won't change direction, it'll just keep moving. Newton's second law that's his first law. The second law is what happens if there are forces. Newton's second law, what is it? F equals what? F equals ma. F equals ma is actually a special form of the law, but it's the one we're going to use almost all the time. Except for in a couple homework problems, you might get a more general form of it then. What does this mean? Well, first of all, what do we mean by F? So F is a force, we'll talk about that, but this is a very specific collection of forces here. This is the net force on some object, whatever that object is. And what does this A mean? It's acceleration. It's the acceleration of the same object, right? This is really important. And this is the mass of that object, of that same object, right? And the reason I'm making a big deal about this is that in almost any problem you encounter in a physics class, there's going to be a whole bunch of forces. Some are acting on this object, some are acting on that object, some are caused by this object. In fact, it turns out that if there's a force acting on an object, there's always an equal amount of force acting by that object on the original object. That's Newton's third law, which is a different law. It says that force of A on B, where A and B are two different objects, is equal to negative the force of B on A. So these are separate physical laws. And I'm really making a big deal about the fact that they're physical laws, right? Everything we've seen in the class so far has been essentially just math and definitions. We've done some demos that involve physical objects in the world, but you sort of take my word for it, like, okay, it's experiencing constant acceleration to gravity. We'll get to that later. So, okay, if you'll accept that that's constant acceleration, and if you'll accept that the ball going down the incline or the sliding block on an incline is moving at constant acceleration, then we can apply those constant acceleration equations and figure out what's going to happen. But now I'm running down stuff that's not just definitions. This isn't just a matter of defining the motion of an object. It's not just a matter of sort of doing a math proof of something that we were already told. These are new facts about the world that didn't have to be true. They're not things we can just define. In other words, the thing that's on the left-hand side of the equation is not the same as the thing that's on the right-hand side of the equation. They have the same value in the same units, but they represent different physical things. The mass of an object is acceleration. The acceleration of an object, right, is the second derivative of its position with respect to time. It's the description of its motion. Whereas F is this abstract thing, this force that we're going to be using to try to describe when accelerations take on, well, when acceleration occurs and why it occurs and what sign it has and what the value is of it. And this is a statement just about these forces over here on their own. And it also is a physical law that didn't have to be true. In some other universe or at some past moment in our universe, it could have been different, right? Although scientists look back in time with telescopes and check to see things look like they're pretty constant, with a few exceptions that are really interesting. But this seems to be something you can count on. These things are always true. Okay, great. So we got our new physical laws. How do we use them? And what sort of forces can we come up with? And also, let's talk about what the units of force is. So just based on this equation, you can figure out what the units must be for force. Oh, if you know what the units of mass are. So what units do we use in this class for mass? Kilograms. That's right. So the units of force, I'll often write it this way. I'll put square brackets around something to say the units of this thing. Well, it's going to have to be kilograms. It's a little messy. Kilograms times meter per second squared. And we're going to give that a name. We're going to call it newtons. Right? So force in this class is represented as newtons, which is the same thing as kilogram meter per second squared. I don't care which one you write down on exams. They're both perfectly valid. Either of these for a force. Right? Great. And there's all kinds of forces we might encounter. We've already encountered one with projectile motion. We talked about gravity. Right? So what kind of forces can we have? Let's make a quick list. Types of forces. Oh, and I might mean two things by types. I might mean what fundamental forces. So there's all kinds of fundamental forces in nature, right? There's gravity, there's electricity and magnetism. Turns out electricity and magnetism are actually manifestations of the same thing. You have a unified theory for those called electromagnetism. There's a weak force. Turns out that the weak force, which is a very short-range force, as the name might suggest, and it's pretty weak, and it happens for very short distances. Turns out that that's also been unified. So it's called electro-weak. It's what since the 70s we refer to it as electro-weak, sort of the same force. And then there's the strong force. And the strong force, yeah, what keeps gluons and what else is in there? Quarks together inside the nucleons, inside a proton or neutron. It also explains how they interact with each other, neutrons and protons, neutrons and neutrons. Anyway, so that's important for nuclear force. So in this class, most of the stuff we're going to deal with are macroscopic, like objects like the size of a person or the desk or things, this little card, things like that. So the only forces we really are dealing with from a fundamental standpoint, really in this class, is gravity and contact forces, like the fact that my hands don't go through the table, and that I experience friction if I try to rub against the table. There can be forces that oppose sliding, right? Or oppose, yeah. Anyway, I'll leave it at that for now. We'll talk about friction a lot next lecture. We'll do a whole lecture, which is actually a lot of fun, believe it or not. And those forces are all mediated by electromagnetism, mostly by electrostatic forces. So really, most of what we're dealing with in an introductory mechanics section of this class, and pretty much for the entire semester, is going to be gravity and electrostatic forces. But when it comes to electrostatic forces, not until you get to 8B are we going to break it down and talk about theories that are specific to electromagnetism. We're going to write down as a charge, there's a repelling charge, and all that stuff. We're not going to deal with that. We're just going to make simplified statements that are extremely accurate to a high degree of precision and accuracy of the macroscopic properties of objects due to the fact that there are these microscopic electrostatic forces. So in other words, we're going to talk about a normal force, or the force of friction, without referring to electricity, or electrical electrostatic force. So now I'll list the types of forces we experience in terms of the sort of objects and the sort of concepts that result in a force that might show up on a problem. Right? Well, one is gravity. Another one is of the types of contact force I just mentioned, so the normal force. In quotes, I'll say normal force. And then there's also friction. And in fact, there's two kinds. There's kinetic and static. So you can have friction forces, whether something's sliding against something else, or even if they're not sliding, if they're just pushing on each other, but they're not sliding yet. Right? You can have both these kinds of friction forces. You can also have force from a spring. Right? You can have a spring that can push or pull. You can have a rope. We'll often call that tension. Tension will be the magnitude of the force that the rope is exerting on the thing on the end of it. Oh, this is in your way. Can I lift this without breaking it? I don't know. Oh. There we go. Amazing. Oh. You know, my microphone always takes a header when I do that. Okay, good. Rope. And ropes, so there's I only know two engineering laws on the top of my head. I think the second one is that you can't move a hole. And once you dig a hole, you can't just move it over, right? So make sure you dig it in the right spot. The first one is you can't push with a rope, all right? And that sounds really stupid, but I guarantee you, students who are very smart, students who are not disciplined in how they keep track of stuff, will put forces pointing the wrong direction through the ropes. It's really easy to get that backwards if you're not careful. So just remember, ropes only pull. Springs can push or pull. So when you use springs, if you stretch a spring, it'll pull back on you, right? If you push on it, it'll push back on you. So springs can exert forces in either direction. So you have to be really thoughtful about where's the equilibrium position of the spring. We'll get to that. But I just want to give you a heads up now. Ropes, though, ropes only pull. You can't push with a rope. At least not an ideal rope. You got a big, really thick rope, maybe you could, but the kind of ropes we deal with this in the class and in the problem are going to assume that they can only pull. That they only exert a force when they're tight, right? So you have ropes, you have springs, you have friction, and normal forces are contact forces, right? Gravity. What else? What other forces? Those are most of the characters that show up. And then, of course, there's just people pushing on things. But we'll usually just sort of think of those as normal forces. Like if I push on the wall, now I'm exerting force on the wall, right? Okay, so these are the kind of forces that will show up. Gravity we've already seen. And the thing is, the way we've dealt with gravity so far is to say, well, if gravity is the only thing acting on this object in the air, then I know what the acceleration is going to be. It's going to be 10 meters per second squared, straight down. But what if there's more forces acting on the object? What if gravity is acting on the object, but I'm pushing on it too, like right now? So right now, I'm exerting a force on this piece of chalk. What direction is the force from my hand to the chalk right now? Straight up. And you know that, right? Because if I let go, it would have fallen down. So you know, you think, oh, because F equals omega, if you let go. If I let go, gravity is the only force acting on the chalk. So one way we can represent this is with a free body diagram. It sounds like a protest song, but what that refers to is a diagram where you just draw the forces acting on a particular object, right? So let's take this piece of chalk. So here's my object, this piece of chalk. I want to use Newton's second law to describe how the forces on it relate to its motion. All right? Well, right now, what's its acceleration? Is the chalk moving at all? No. So what's its acceleration? It's zero. No matter which direction I choose, X or Y, however I define it. So let's define this to be my y-axis. And let's go ahead and say, here's my chalk. Here's my free body diagram for the chalk. All right? Now, free body diagrams are useful for Newton's second law. So this is important for figuring out what F net is. Not Newton's third law, Newton's second law. The forces in Newton's third law are different in general. Well, it'll always be different. The collection will be different. Some will be the same, some will be different. Between those two equations. So we're going to focus on Newton's second law right now. We're going to use Newton's second law. In order to relate the acceleration to the net force. So how do you get the net force? Well, first what you do is figure out all the forces acting on the object. So this is a really simple situation. The thing's not accelerating. It's experiencing a force of gravity, which points straight down. A force from my hand that points straight up. So what I do is I draw a little point, and that represents the chalk. Later in this class, we're going to be dealing with torques, where you've got forces acting on a certain part of the chalk that can spin the chalk. Right now, we're not going to worry about torque. We're just going to worry about the forces acting on this object, and we're not going to worry about where the force is acting on the object. All we care about is the forces acting on this object. So the free body diagram of the chalk includes the force due to gravity. And to be really clear, this is the force of the Earth's gravity on the chalk, right? Pointing straight down. It turns out, I haven't told you this yet. Well, actually, it did come up a couple times in the lectures before, but formally we haven't introduced this.